Hey everyone, today we'll be talking about Proton NMR. Our topics will be talking about the concept behind NMR, looking at the NMR spectrum, and going over some key terms in order to help determine the molecular structure. So for our first topic today, we'll be going over NMR spectroscopy. And the basis behind this type of spectroscopy is the idea that nuclei have something called a spin. And of course, we know that they're electrically charged. And this is, if you remember, nuclei contain protons and neutrons. And if you were to take a sample of nuclei, as shown here, and apply like this external magnetic field going in this direction, you would find that this would cause the spins of the nuclei to abruptly and relatively sharply align. So this forms something called parallel and anti-parallel spins. And so again, let's say this is the direction of our external magnetic field applied against or applied onto these nuclei here. This creates parallel and anti-parallel spins in which, say, if the spin is going in the opposite direction of the magnetic field, you would get a -1/2 spin, and this is considered anti-parallel, versus if the spins align parallel to the magnetic field in the same direction as shown here, you get a +1/2 spin, and this is considered parallel to the magnetic field. And this has to do a lot with the energy states as well. So when it goes against the magnetic field, the spins are opposite. This actually leads to a more excited energy state versus something that is aligned with the magnetic field parallel, and this is considered a ground state where the energy is not as high. And so in the NMR spectrum, we tend to measure the oscillation between this ground state and excited state to generate what we see in the spectrum, which we'll look at later. And something to keep in mind is if you increase the magnetic field strength at the nucleus, so if you were to increase the strength of this magnetic field here, this leads to an increase in the energy of the spin states. And another name in general for H-Nmr is also called a Proton NMR, which you might referred to. So this is the NMR spectrum shown here, and again, this is what is registered in the spectrum. Really the goal of the NMR process or NMR spectroscopy is to understand the molecular structure by considering these four things over here, and a lot of it has to do with the location and the number of protons and hydrogens attached that we're looking at. Let's take a look here and label the axes. So on the x-axis, we have something called the spin flip energy, and this is actually measured in units of ppm. Whereas on the y-axis, we have something called the intensity of the signal, or the photon quantity, and these are the main axes of the spectrum. And something else I want to highlight is something called TMS. This is tetramethylsilane, and this is simply just a reference point. So if you see this on a lot of the spectrums that you might take a look at, then it's just a reference point. It's not really part of the molecule. So when you look at proton equivalency, the main thing we're considering is how many signals we see in the spectrum. And the number of signals that register in the spectrum indicate the number of non-equivalent proton types. And what that means is we're looking for protons that have different magnetic environments. So if you have protons with the same magnetic environment, this means that they are equivalent protons. And if you have equivalent protons, this registers as one signal, or the same signal. So, for example, let's take a look again at ethanol. So here we have a methyl, we have an aldehyde. And this hydrogen, let's take a look at this hydrogen specifically. I'm going to label it HA. This hydrogen is attached to a carbon, this carbon is attached to a carbon, and this carbon is attached to an oxygen and a hydrogen. So then let's look at this hydrogen here. This one is essentially the same thing as this hydrogen here in the sense that it's attached to the same carbon, which is attached to the same carbon and oxygen and hydrogen. So if you can trace their pathways and find that the pathway of the hydrogen is the same in terms of its connectivity, then it's a good indicator that the protons are equivalent. Same thing with this hydrogen here. So these three are actually technically equivalent in the sense that they are feeling the same magnetic environment. This one, however, differs from the rest of these hydrogens in the sense that it's not connected to the same carbon as this one, and it's not feeling the same type of magnetic environment as the rest. So I would consider this HB here. And if you look over at the spectrum, you'll expect to see two signals since there are two types of non-equivalent protons. And so indeed we do see two signals here. Here's the signal for the methyl hydrogens, and then here's the signal for the methyl aldehyde. All right, so now let's go into chemical shifts. So chemical shifts are all about not the number of signals that we have, but rather where they are along the axis, the x-axis. So it's really to do with the position of the signals. And here we consider a lot to do with electronegativity. So when you have a higher electronegativity of atoms near the hydrogen that you're looking at or considering, this leads to a decrease in electron density around the hydrogen. And so let's take a look here at this aldehyde portion of ethanol, and you'll see that this oxygen, of course, as you remember, is very electronegative. So it's going to pull a lot of the electrons towards itself, from the carbon, but also the hydrogen will feel like this kind of shifting away of electrons. And now, if you imagine there's like a lot of electrons around here, but all of it's getting shifted that way towards the oxygen, now it's going to feel a little bit naked. It's going to feel a little bit bare since these electrons are being pulled away, and it's not going to have as much protection. So when you have a higher electronegativity of atoms near the hydrogen, this decreases the electron density around the hydrogen, and this leads to a decrease in something called shielding. And the shielding is what I referred to when I talked about the electron clouds surrounding the molecule, or protection by the electrons around the hydrogen. And of course, kind of similar to inductive effects that we talked about in an earlier video, if you have a highly electronegative atom that is farther and farther away from the hydrogen that we're considering, then this leads to a decreased effect of the electrons being pulled away. So if I were to tie this back to the NMR spectrum, something important to remember is if you have more deshielding, this actually leads to a higher chemical shift. So this over here represents more deshielding, which is equal to a higher chemical shift. So it's 10 here as opposed to only 2 over here. And so the reason for this is if you can just imagine, like if you have a molecule or an atom that's very deshielded, not as much protection, if you apply this external magnetic field to it, it's going to cause a much greater effect on the hydrogen nucleus than if it were to be more protected by the electrons around it. So I just try to remember it by deshielding leads to it being more naked and bare, so now it's more susceptible to influences externally, and so this causes a greater chemical shift. Okay, so deshielding is down here. This is downfield in the NMR spectrum, and here we have less deshielding, so this means that it doesn't shift as far. So chemical shift again is just how far along it moves on the x-axis. The next thing I want to consider is integration. So integration refers to the intensity of the signals. And the important thing to remember here is that we're measuring the peak area, not necessarily the peak height. And the way you figure out what the integration is, or what the integral is you consider the proton ratios. So again, I have here ethanol, and we're going to look at first how many protons compose each set of equivalent protons. So if you remember, we determined that these were equivalents and this one was another set of equivalent hydrogens. So what we're going to do, and the way to do it, is you count how many protons are equivalent to each other in each group. So in the HA group, we see that we have 3 protons that are equivalent, whereas here we only have 1 proton that's equivalent for the HB group. So the integral that we assign has to do with the ratio of the protons. And something to keep in mind is we always want to simplify our ratios to the smallest number value. So we always want to set it to 1 as our lowest value. So if we were to look at something along the spectrum at our 9.8 ppm, this is actually where the HB, or the aldehyde hydrogen, lies. We see that we have 1 proton and we have 3 protons at the 2.2 chemical shift, which is this one over here representing these hydrogens. And so the ratio of this one to this one is 1 to 3. We want our lowest integer to be 1, which we already have that here, so we don't need to divide or simplify anything further. So our integral for this is actually 1 here and 3 here. So in some cases, you'll find that the integral represents the same value as the number of protons and hydrogens that are in the group, but this is not always the case, so just keep that in mind. So the last thing I want to touch on is something called signal splitting, and this usually has to do with the proton feeling more than one magnetic environment, and so this leads to something called, this leads to a lot of little different chemical shifts. It's still all considered as one signal, or one group of signals, I guess you could say, but it's basically within the signal, it splits into little ones. So that's how you can kind of think of it. And as I mentioned a bit earlier, this multiple magnetic environment refers to the external magnetic environment that you apply. It refers to like the magnetic environment from neighboring nuclei. It just feels a lot of things. So some important things to remember in terms of signal splitting has to do with these rules I've outlined below. So the first thing we want to look at is a proton with n number of neighbors splits into n plus 1 lines. So, and to determine the neighboring protons, you basically have to look at single bonds. So double bonds don't really matter as much, but single bonds are really where you start and count from. So let's take a look at this hydrogen here. Okay, I'm going to take a look at this one. So for our neighbors, we will look at hydrogens that are not equivalent to it and that are at least 3 bonds away. Okay, so Alright, so the last thing I want to touch on is signal splitting. So signal splitting refers to when a proton basically feels more than one magnetic environment, and this magnetic environment can be due to neighboring nuclei's magnetic environments as well as the external environment, magnetic environment that we apply to the nucleus. And this leads to little different chemical shifts. And this is all still considered one signal. It looks a little bit like this. This is what signal splitting looks like. It's still all considered one like main signal. However, within that signal, it splits into little ones. So that's how you can think of it. And so some rules to really keep in mind when you look at signal splitting is that the first one is that a proton with a certain number of neighbors will split into n plus 1 lines. So when you're trying to determine whether protons are neighbors with each other versus equivalent protons, just remember that neighboring protons are 3 single bonds away or less, and they cannot be equivalent protons in the same group. So let's take a look at this green hydrogen here. So let's take a look at this and see how many neighbors it has. So starting from this hydrogen, I'm going to count 3 single bonds away. 1, 2, 3. So this is 3 single bonds away from this blue hydrogen here. So this blue hydrogen would be considered a neighbor of this hydrogen, the green one. However, these other green hydrogens are not considered neighbors since they are all equivalent, so we don't consider equivalent hydrogens to be neighboring candidates. Okay, so here we have one neighbor. Let's go ahead and take a look at this one since these are equivalent. 1, 2, 3. This one's also a neighbor of this green hydrogen. So we would say that this one has 2 neighbors And as a result, for this rule, n is equal to 2, and it will split into n plus 1 lines, and so it will split into 3 lines. So if we were to look at our NMR spectrum, we see that there's a split into 3 lines here. Okay, so that's one way to think of it. Let's go ahead and look at these blue hydrogens here and work backwards now. I'm going to change my pen color. So let's take a look at this hydrogen and count how many single bonds away. So 1, 2, 3. So this is 3 single bonds away. And again, we have one neighbor here for this hydrogen. And since this hydrogen is equivalent to the other green ones, we're going to go ahead and count those also as neighbors for this one. So as a result, we have 1, 2, 3, 1, 2, 3, 1, 2. So we have 3 neighbors for this hydrogen. So this one has 3 neighbors. And as a result, we're going to have a split into 4. We're going to have a split into 4 lines in the signal. Okay, so we have 1, 2, 3, 4 as shown here. And you don't really need to consider like both of these each having 4 splits like in separate places because they are equivalent hydrogens. So we only really need to consider, start by looking at one hydrogen in each equivalent proton group and then count 3 signals away. And that's what you would see in the spectrum. Okay? And then the last thing I want to highlight is this methyl group here. So the reason we don't see a split in this one is the fact that this doesn't actually have any neighboring hydrogens. And the reason for that is if you count the signals, the rule is 3 single bonds, 1, 2, 3, we actually get to a carbon. We don't really quite make it to another hydrogen, and so there's no neighboring molecules for this methyl hydrogen over here. Okay? And so just to move on with the rest of this slide, you'll see that OH and NH bonds are usually singlets, not always, but that's a good rule to keep in mind. And just remember that benzene ring, since it's very, very, has a lot of resonance and a lot of electron delocalization and things like that, and the molecules are very equivalent to each other, they can actually all couple with each other. And all right, the last thing I want to highlight is something called magnetic induction. And magnetic induction refers to when one magnetic field causes another magnetic field. And so this actually is used more in reference to when you have pi electrons to work with. So if we were to apply an external magnetic field, this often causes pi electrons, such as in like something like a carbon-carbon double bond. These pi electrons will shift around and start to simply move throughout the molecule. And since these pi electrons have their own negative charges, this actually causes the pi electrons to start forming their own magnetic field. And so an external magnetic field is applied to the molecule. The pi electrons then, as a result, are generating their own magnetic field as a result of the feeling from this external field. So that's kind of the process. It's not like a huge concept, but it's helpful to know so you can understand how magnetic fields kind of relate to one another and how it affects different parts of the molecule. Okay, and so the last thing I want to touch on is these benzene rings and aldehydes. So you'll see that the benzene ring tends to form something called a multiplet. I'm going to write that down here. And this means that there's a lot of like crazy little singlets happening around. And this causes it to form a lot of signal splitting, basically. And you'll find that benzene ring shifts are usually around 6.5 to 8 ppm. And the reason I tell you this information is so that it can help you narrow down what your types of molecules that you should be considering when you're trying to build your molecular structure. And then for aldehyde, you'll find that its chemical shift usually falls around 9.5 to 11. So this represents the aldehyde hydrogen here. This represents that hydrogen. So that's what you might see. You might see a very intense, tall, single singlet at around 9.5 to 11, and that's usually indicative of an aldehyde. So these are some tips and tricks to help you, again, speed up the process of identifying what molecule you might be working with and trying to see what types of hydrogens are involved.